We are now prepared to present a method of constructing a confidence interval about the population proportion P. Constructing a 1 minus alpha times 100% confidence interval for a population proportion. Suppose that a simple random sample of size n is taken from a population or the data are the result of a randomized experiment. A 1 minus alpha times 100% confidence interval for P is given by the following quantities. We have the lower bound, which is the point estimate minus the critical z value, times the square root of the point estimate times 1 minus the point estimate over n. And the upper bound is the same formula, only the difference now is the upper bound is taking the point estimate plus the critical z value times the square root of the point estimate times 1 minus the point estimate over n. Now note, it must be the case that n times the point estimate times 1 minus the point estimate must be greater than or equal to 10, and n, or the sample size, must be less than or equal to 5% of the population to construct this interval. We're going to use the point estimate, p hat, in place of p in the standard deviation. This is because p is unknown, and the point estimate is the best point estimate of p. So let's take a look at an example here. In this next example, we're going to be constructing a confidence interval for a population proportion. In the Parent Teen Cell Phone Survey conducted by Princeton Survey Research Associates International, 800 randomly sampled 16 to 17-year-olds living in the United States were asked whether they have ever used their cell phone to text while driving. Of the 800 teenagers surveyed, 272 indicated that they text while driving. We want to obtain a 95% confidence interval for the proportion of 16 to 17-year-olds who text while driving. So for step 1, there are X equals 272 successes, meaning that these are the teens who said they text while driving, out of the N, which is equal to 800 individuals in the survey. So what we want to do is we want to find the point estimate. Well, the point estimate is the following. We know that X being 272, and then we're going to divide it by the sample size of 800, gives us a point estimate of 0.34. Okay, now in step number 2, they want us to verify the conditions. So, first and foremost, before we do that, we need to take the value of the sample size, which is n, and that is 800. And then we're going to multiply it by the point estimate times 1 minus the point estimate to determine whether it is greater than or equal to 10. So 800 times 0.34 times 1 minus 0.34 gives us 179.52, which verifies that it's greater than or equal to 10. Now we need to verify the fact that n, or the sample size, is less than 5% of the population. Now, we know that there are more than 1 million teenagers 16 to 17 years of age in the United States. So that means if we took 800, which is our sample size, we would know that it's going to be less than or equal to 5% of the million teenagers. So therefore, we would say that 800 is going to be less than that 5,000. So our sample size is definitely less than 5% of the population size. Therefore, the independence requirement is satisfied because of these two. Now, we need to determine the critical value, which is z alpha divided by 2. Okay, now with a 95% level of confidence, what we need to do is we need to determine what is alpha first. Well, alpha is taken 100% minus 95%, which gives us 5. And therefore, 5% as a decimal is 0.05. Okay, now we need to find that critical value. Well, z alpha divided by 2, well, what do we find for alpha? Alpha is 0.05. So 0.05 divided by 2 gives us 0.025. Now, if you recall, whenever we have z with a subscript of alpha, this represents the area that's to the right of the critical value. What I mean by that is, if you take a look over here, the value here, this area, is to the right of the z critical value, which is 0.025. So if we wanted to determine what is the critical value, then we would need to look at our table and find the area that's to the left of the z critical value. That means that we need to take 1 and subtract 0.025, which gives us 0.975. So we're going to use this area to find the critical z value. So we're going to go ahead and look at the table. So let's open up our table. So when we open up our table for z values, okay, we're going to search for the area of 0.9750, and there it is. So that means we end up getting a critical value of 1.96, and that's how we get 1.96. And again, what that tells us is that, again, 0.025 is the area to the right of the critical z value 1.96. So therefore, this z down here, this value, represents positive 1.96. Okay? Now what we want to do is we want to find the lower and upper bounds, where we know that the point estimate is 0.34. We know that our critical z value is 1.96, and the sample size is 100. So to find the lower bound, what we're going to do is now we're going to plug in the particular values. Okay, so we know that the point estimate is 0.34. We know that the critical value is 1.96. And we know the sample size is 800. So we're going to go ahead and fill in the information to find the lower bound. So plugging that in, again, we know that P is 0.34. We know the critical value is 1.96. And we know that the sample size is 800. So now let's go ahead and do this on our calculator. Let's just go ahead and do this part here. So we're going to take 1.96. Okay, and then we're going to multiply it by the second square root. We're going to contain the numerator, so we have parentheses, and then we have 0.34 times 1 minus 0.34. And then we're going to add 2 parentheses to close this one and that one. And then we're going to divide by 800. Okay, and so that gives us 0.033. Okay, so that means if we take 0.34 and subtract 0.33, we should get 0.307. Let's just verify that here. So we're going to take 0.34, and then we're going to subtract this answer, second answer, to make sure that when we round this to 3 decimal places, we get 0.307. So that represents our lower bound. Okay, now we're going to take our upper bound. So the only thing that changes now is the addition sign. So again, what we're going to do is, now we're going to take 0.34, and then we're going to add 1.96, and then multiply it by the square root of 0.34 times 1 minus 0.34 over 800. So let's go ahead and do that again. So we're going to take 1.96, multiply that by the second square root of left parenthesis 0.34 times parenthesis 1 minus 0.34, one parenthesis, another parenthesis, and then divide that by 800. Okay, so that gives us 0.033 again, correct? So that's what we did earlier. So now what we're going to do is we're going to take 0.34 and multiply and add it to 0.033. So if we take 0.34, okay, and then add this answer here, so we're going to say second answer, it should give us 0.373, which that's what it gives us here, and that represents our upper bound. So the interpretation is going to be the following. We are 95% confident that the proportion of 16 to 17-year-olds who text while driving is between 0.307 and 0.373. It is important to remember the correct interpretation of a confidence interval. The statement 95% confident means that if 1,000 samples of size 800 were taken, we would expect 950 of the intervals to contain the parameter p, while 50 will not. Unfortunately, we cannot know whether the interval we constructed is one of the 950 intervals that contains p or one of the 50 that does not contain p. Now also note, we report the interval as lower bound 0.307, upper bound is 0.373. Now in some other areas, whether it's another textbook, we will also use interval notation. You have parenthesis, the lower bound is 0.307, comma, the upper bound is 0.373 with your right parenthesis.